So the plan for today is to move on and touch on maybe the first couple sections of chapter 12, and we'll come back to chapter 12 later in the semester as well. But this is a good chance to let us apply some of the proof techniques that we've looked at so far to kind of the main object of study in mathematics, which is functions. So we'll be working with the worksheet on functions today, which you had a reading quiz about last week. So there was no reading quiz for today. But so before we get started on this worksheet, does anybody have any questions in general? So there is a early semester evaluation up online. So thanks to everybody who sent that in. Right now, we've got 75% response rate. So I said if we get 80% response rate, we get 2 bonus points on your first exam. So I think we need 2 more people to respond to that. So if you haven't responded to that yet, please do so. And thanks for the comments that I've gotten so far. It's all anonymous, so don't. So feel free just kind of sharing your honest opinion about things. Okay. So if there aren't any other questions, then we'll begin today talking about functions. So as you probably are aware, a function is a mapping. It's a relationship that has one special property, which is every element in the domain, every input gets exactly one output. And so relating to functions are ideas of domain, codomain, and range. And this is hopefully mainly a revisiting of some things that you've already studied in calculus and whatnot. So for question number 1, f is a map from R to R, where f of x is equal to x squared, right? This certainly is an example of a function. The domain and the codomain are usually not very difficult to specify because they're given to us. But the thing that I do want to make a distinction about is this distinction between codomain and range. So in this example, the range is not equal to the codomain. In fact, what would the range be for this function? If you don't want to talk, you're welcome to chat in your ideas as well.
Any r greater than 0, greater than equal to 0?
That's right. Yeah. So we want to include 0 in here. That's right. So this would be, sometimes we write that r plus. I should just say this. R plus is used to denote the set of, we'll call them y here since they're outputs, would be the set of all y. Set of all y in R such that y is greater than or equal to 0. You could write it out either way. You could write it out using an inequality or interval notation. Yeah. So the important thing here is that the range, right, is always going to be some subset of the codomain, possibly all of it. Okay. Any questions about these terms? Okay, then this one was on the quiz from last time, but maybe we could just take a look at this one in D, which is a map. Oh, I skipped over B. I should just say this function, this mapping is not a function here. Anyone know why not?
You can get an invalid number or
That's
result.
Right. Yeah, and so f is a function from A to B, and this is telling us that for every element in the domain, we should get an output. And this is not a function since f, in this case, which value in this domain wouldn't give me a defined output. What x value is going to give us some problems if I try and evaluate this function? 1. Yeah. So actually, there is no element in the codomain which is mapped from the element 1 which is in the domain. So this would not be a function, but if we define it as a map from r minus 0, not 0, excuse me, r minus the value 1, then this would be a function as if we were to modify the domain. So it's not an issue of getting one output. The issue is that it needs to be defined for all values in the set. Okay, so in D, what we're mapping here is from the power set of X, excluding the empty set, which would be in the power set, into the natural numbers, where we're going to define this map as the cardinality of the set. And let me just say the cardinality of a set is just how many elements are in the set. So when I say absolute A, we use the same sort of absolute value notation. This is telling me how many elements are in A. Okay, and that's just defined as the cardinality. So we've got the domain here is the power set of X minus the empty set. And the range is the natural numbers. Okay, so this means 1, 2, 3, 4, 5, etc. Nope. Codomain is the natural numbers. And we want to figure out what is the range of this map. Okay, and again, this map is defined by, it's going to take every element of the power set of X, which is a set itself, and it's going to count up how many elements are in that set. So what would the range of this be? Anybody have any thoughts? Feel free to chat them. I know the answer, but that doesn't help. I'd like to know if you know the answer. Okay, then we'll take. Sorry, someone had a suggestion. Brandon, was that you or John?
Brandon.
Brandon, yeah.
The cardinality of like all cardinalities of each set in the power set.
Yeah, and so it might help to kind of think about, well, what is the power set of X going to look like? And so the power set of X in general, we could say is the empty set, and then it's going to be all of the set of single elements and so on, right? And then you would have sets of 2 elements and so on. And so what this map is going to do, it's going to take each of these things. It's going to exclude this one, so we're going to ignore that. But it would take this element over here, and under this map of C, it's going to take this element and map it to its cardinality. And what would the cardinality of the set that contains 1 be?
1.
1, right? There's 1 element in the set 1. And then it does the same for other things. So it would take this and map this also to what is the cardinality of 2, and that also is 1. Okay, so the cardinality is counting how many elements are in the set. So the range is definitely going to include 1, right? It's going to include 2 because I do have subsets of X that have 2 elements in it. And we're going to map to 3 and to 4 and to 5 because I can come up with subsets that have 3, 4, or 5 elements. What is the maximum sized set that's going to be in the power set?
100.
100, right? And that would be X itself. So X itself is a subset of itself. So X is in the power set. So if we were to map X, it would get mapped to 100 because there are 100 elements in the set X. So that would be the range for that map. So we don't map onto all of the natural numbers, but we map to the first 100 natural numbers.
So the range itself is a set.
The range is going to be a set, yes. The domain, codomain, range, these are all sets. Yep. Okay, any questions? So what we need to require is that each element gets mapped to one thing. So every set has exactly one cardinality, so we're okay. The thing that I do want to think about next is this function is not what we would call one-to-one. It's not in, well, that's not what, it's not an injective map is really what I mean to say. Because we have some elements in here, like the set 1 and the set 2, they have the same output. So that's not an issue. If different inputs get the same output, that's okay. The issue that we want to watch out for is one input getting different outputs. Okay, so that was kind of a review of some of the things that you looked at last week. Any questions about these terms? Okay. So next up is this notion of what does it mean for a map to be one-to-one, which is how you typically refer to this, like in a pre-calc calculus class. In mathematics, if you want to sound fancier, we call that an injective map. And so what it means for a function to be one-to-one is exactly a counterexample that we just saw, and that is every input gets mapped to exactly one output. That's what it means to be a function. And each of, if two inputs have the same output value, then they have to be equal to each other. Okay, so in other words, what we can't have is two different inputs being mapped to the same output. So in other words, of saying this is each distinct input gets a distinct output, or in other words, no two distinct inputs have same image. Okay, so we say image. Okay, image refers to its output by the map. So injective is a definition, and it's a conditional definition. So one way that we can write this out is by thinking about if x is not equal to y, then f of x is not equal to y. So if the inputs are not equal to each other, then it must follow that the outputs are not equal to each other. Okay, so I don't want to get into the proof aspect of it just yet. I want to just maybe think about our intuition for these things, since these are mostly not new terminology, right? We've thought about one-to-one functions when we think about whether or not something has an inverse and things like that. So I'm going to break us up into groups, and I would just like you to go through, question 2. So question 2 has a bunch of functions. I'm not asking, is it a function? What is the domain, codomain, range? What I'm interested in is the function injective? Is it one-to-one? And then if you think it is not one-to-one, maybe explain why not. If you think it is one-to-one, maybe try and explain why. But I would say at a first pass, just kind of go through the list and indicate whether you think they are injective or not. And then we'll compare our notes as a class. But any questions? So try not to belabor it too much. Don't want to get too deep into it besides just looking on the surface. you probably are familiar with some of these functions. Are they injective or not? So maybe we'll take about 10 minutes to discuss that in groups. Okay, welcome back, everyone. Okay, so sorry, I got some requests for a question just as I was closing things, so I don't want to disregard any of those. Like, we can kind of talk to them, talk things out all together. So I just have a poll. I'll just launch it just to see what you guys thought. And if there's agreement, then we'll move on to the next one. And if there's not, we'll discuss. So this is in regards to A. Did you think that the function in A was injective or not? You might have already submitted your answer before I said which one we were talking about. Okay, good. So we got just about everybody in. That's everybody. So here were the results from that one. And there were a couple that came in right away as yes, definitely, before I said which one we're thinking about. So I don't know if those were opinions that wanted to change. But yes, so A is not injective. And what's a proof of why that is not injective? Anyone have an idea?
Every negative value that's input has the same as its corresponding, has the same output as its corresponding positive value.
That's right. So for example, f of 1 is 1, f of minus 1 is 1. They equal each other, although 1 and minus 1 are not equal to each other. So in order to prove that something is not injective, you just need to provide one counter example that's sufficient. In order to prove that it is injective, that's a little bit trickier, right? Because then you would need to show that for all inputs, they all get a unique output. Any questions about that one? Okay, let's relaunch this one in regards to B now. Did you think that B was injective or not? Okay, we have unanimous no, definitely, so I don't think we need to belabor that one. And you could use the same counter example from B, right? Okay. About C, let me open this up again. This is now for j of x is equal to x cubed. Okay, so that seems to be coming back overwhelmingly as injective. Okay, that's great. We'll table that for a second as to why that might be true. But the old like pre-calculus way of doing this is to say, here's a graph. This passes the so-called horizontal line test. So this is a really, really informal way of doing it. We want to formalize that to prove that a little bit more carefully. But you may recall the horizontal line test as a test for one-to-oneness, where something like x squared, right, clearly violates that. Okay, then we are on D. What do you guys think about D? Okay, so these are the votes so far. So this one's a little bit more split. So maybe we should talk about it just to see if there are any questions. So someone want to share how you came up with your yes or no?
I just plugged it into a graphing function and showed that it didn't pass the horizontal line test.
Okay, yeah, so if you graph this, I don't know exactly where I think maybe it looks something like this, more or less.
Yeah,
So you get
basically
this little
that.
wiggle in the middle, and in particular, yeah, there are multiple points where k of x is equal to 0. That's right. So for example, k of 0 is equal to 0, k of 1 is equal to 0. Yeah, and yeah, so maybe I have not quite the exact graph, but in any case, we have 2 points, 2 different values of x that are both being mapped to 0, so that would violate the one-to-oneness. Any questions? Okay, so let's see what happened with this power set. So if you got to the point where you didn't have a chance to think about it amongst your group, you can still chime in. I don't know how far actually all of the groups might have gotten here. Okay, and this is another power set problem. So let's show you where we're at with this one. So we had 3 no definitelys, yeah, and mostly everybody else kind of was leaning one way or the other or had no idea. Okay, so this seems like a good one to talk about then. Who thinks they got this? There were a couple no definitely people. Any one of the no definitelys want to take a shot at this? So this is just to be sure we're clear with the map. So we have the set of real numbers, and then we have P, F of R are all of the finite sets of the real numbers. Okay, tons of those. But there are a finite number of elements. So for each one of these sets, we're just going to map the set to the product of all of the elements of the set. So in order to find a counterexample, can you think of 2 subsets of R whose elements have the same product?
That'd be like the set of 1 and 2 and -1, -2.
So, right, so by this map, here's a set 1, 2. It's a finite subset of the reals. So it's in our domain. And this map Q is going to take this and map it to the set 1 times 2, which is 2. That's exactly right. And so we can think of a second subset, which is different than the first one, say, which is the subset that contains -1 and -2. And this element would have the same output. So this would therefore violate the notion that this would be 1-to-1. So this is also no as far as 1-to-1 goes. So there were some unsureness on that. Are there any questions? Okay, and then
Sorry, I had a question.
yeah, sure.
So the F above the power set P, is that like always the notation for power sets of just the finite subsets?
So yeah, that is the notation when you put the F as a superscript on the power set. Yeah, that is pretty commonly used to denote all finite subsets of that given set. Yeah.
Okay, thanks.
Okay. Then in F is dealing with this floor function, right, which is different than rounding. It just says, you know, pick the next closest integer, which is less than it. So we've got some examples here. So let me open up the poll again for this one, just to hear what you all were thinking. So this is for F now. Awesome. Thanks for those. And here are the results from that one. So for someone want to share the counter example. So this one is not injective as well. That is correct. And what's a good counter example for that?
Well, 3.14 and 3.15 would both round to 3.
Yep. Right, so we have like a whole infinite number of things that are all mapping to 3. So that shouldn't happen if we have an injective map. Different inputs should get different outputs. Okay, so what about if instead of defining this from real numbers into integers, what if we define it, we restrict our domain to just integers? Let's get a poll on that one. Okay, so here were the results from that poll. So a little bit divided here. If A is a real, excuse me, if A is an integer, then what is R of A going to equal? So the floor function is what is the next closest integer that is not greater than it. So for example, like what would R of 1 be?
B1.
B1. R of 2 would be
2.
2. R of minus 5 is
-5.
minus 5, right? So this is really, if we restrict this to just the integers, it's really just like the identity function, right? So this one is, in fact, injective. The only way that two integers can have the same integer, which is not, you know, next closest but not greater than it, is if those are the same integers. Okay, and now in H, we can take a look at more abstract looking function where our input is not numbers, but we're going to deal with people, and our output is not a number, but it's going to be some string of letters. Okay, so here were the responses so far for this one. Does anyone have a counter example? Alex, we're here. Are you,
Yeah, hello.
what are your initials, Alex?
AS?
All right, anybody else in here with AS?
Yeah, you.
There we go. So there's our violation of that one-to-oneness, right? Two different people have the same initials. Okay. Okay, good. So what I want to talk about, so I just wanted to kind of build some intuition about what properties are we looking for when we're trying to determine injectiveness. And now let's think about how we can show this a little bit more formally. So we've talked about how we can disprove it, but just by giving one counter example. If we want to prove something more formally, to say that a function is injective, that's where recognizing the definition as a conditional statement. So we're really trying to prove a conditional statement when we're trying to prove that a function is injective. And so the if P then Q, you can read it as if X is not equal to Y, then the output shouldn't be equal to each other. So we have three proof techniques that we've been thinking about. We can use any one of them to prove that a map is injective. If we were using direct proof, right, we would start by suppose P is true, suppose that we have two elements in our domain that are not equal to each other. And then ultimately what we'd like to show is that therefore their outputs are not equal to each other. If you do it by contrapositive, remember, then this would say we want to show if not Q, then not P. So in this case, we start by assuming not Q, which is two outputs are equal to each other. And then we want to show that if two outputs are equal to each other, that has to imply X is equal to Y. And so out of the ways that oftentimes we prove injectiveness, I would say proof by contrapositive is the more common way of doing it as opposed to direct proof. But you can use either. And there's always the option of proof by contradiction. Again, I would say that proof by contradiction tends to be maybe the least elegant way of doing it. But you could certainly start by assuming a function is not injective. And so what would it mean to assume a function is not injective would mean we have two different inputs that give me the same output. And then from this assumption, you need to show that this leads to some contradiction. So we can use any one of these proof techniques to prove injectiveness. So let me revisit C and just to see what this would look like. So let's erase this horizontal line test since that's a little bit more informal and try and prove this formally. And so I'm going to do this by contrapositive. So let's suppose that J of X is equal to J of Y. Okay, which is the not Q. Okay, then this would imply that then X cubed is equal to Y cubed. And if we're trying to do this by contrapositive, then what we're trying to get to is, okay, well, therefore we see that X is equal to Y. So we kind of know where we should start if we're using contrapositive. We kind of know where we want to end. And so the question is, what can I do in between my first couple of sentences to get to the last sentence? So going from X cubed equals Y cubed, how do you think we can take that equation and get to the conclusion that X has to equal Y?
Take the cube root of both sides.
You can take the cube root of both sides. Exactly. Thank you. So we have the cube root of X cubed is equal to the cube root of Y cubed. Therefore, X is equal to Y, right? And so that would be, it doesn't need to be, usually they're not very long proofs, and usually it's just like an algebra equation in disguise here. So it's a little bit easier to do contrapositive because it's a little bit easier to start by setting two outputs equal to each other and then do some algebra to show that the two inputs have to be equal to each other. Any questions? Okay, so I'm gonna bypass 3 for a second. And so question 4 is dealing exactly with these sorts of proofs of injectiveness. So let's practice some of these. So we'll start with 4A. So 4A is, okay, we've got some map F, which is not even specified here. It's some map from the real numbers to the real numbers. C is some constant real number. And then we're going to define H as we take whatever F does and we add C to it. So the claim here is if F is injected, then H is injective. Let me just put this on a New page. Okay, so I think this was the problem. So just to set up some initial work here, our P is if F is injective. And our Q is H is injective. So we've got different ways of doing this. We're going to prove that P implies Q by direct proof, okay? Meaning how these look right should be, we're going to suppose P dot dot dot, and then hopefully in the end get that therefore Q. So that's how direct proof works in general. So I'll write the proof in black. So this is kind of some scratch work on the side. So if I'm going to do this by direct proof, then yes, we start here with suppose P, which is F is injective. And then again, what we're hoping to show now is statement Q, which is that H is injective. So in other words, what we want to show in order to prove injectiveness, there's a little bit of scratch work. I'll just put over here. And so the way that we can prove injectiveness is by the contrapositive would be to say, if we assume the outputs are equal, that has to imply the two inputs are equal. So we're going to suppose F is injective, and we want to show that Q is also injective. So we're going to hope to show this is what we want to get to in the end. So that would be our statement for Q. So we can say, let's let so this is how we start to prove that the map H is injective, right? So let's pick two elements in the domain of H, and let's assume that they both give me the same output. The only way this map is injective is if that has to imply that X and Y are the same. Okay, so at this point, right, we've got H of X is equal to H of Y. And so what can we do with this line? What do you think makes sense to try next?
Subtract C.
Yeah, so we can take this part over here and subtract C from both sides of that equation. So if f of X plus C equals f of Y plus C, then we know that f of X equals f of Y. And so what can we say if f of X is equal to f of Y?
that y equals x, right?
Yeah, and why is that?
Because f of x is just a function that gives you y, and f of y is just a function that gives you x.
So yeah, we'd like to say that this is going to imply that x is equal to y. So what's the justification from going from this sentence over here that we have down to here?
We're assuming that f is injective.
That's right. It's this first assumption over here. So if f is injective and I have two inputs that give me the same output, if this is injective, then that has to imply x is equal to y.
So when you do say something about inverses, take the inverse of each side.
We don't need to define, we haven't defined inverses yet. And in fact, yeah, we can't define inverses until we define composition of function. So we're not quite at the, that we've seen them before. Like in this class, we're not quite at the point where we can introduce an inverse. We need a little bit more machinery to introduce formally. So I'm not allowed to apply an inverse to both sides, but I don't have to solve this because we suppose that f is injective. And so if f is injective, then it definitely means if f of x equals f of y, x has to equal y. And that's what we want to show here. I want to show that if h of x is equal to h of y, that it has to imply x equals y. So we started with setting h of x equals h of y, just to take us through the logic. And then we saw, well, h of x equals h of y, that implies f of x also has to equal f of y. And now, since we assumed f is injective, f of x equals f of y is going to imply x is equal to y. And again, the reason why we can claim this is since f is injective, if f of x equals f of y, then we know x is equal to y. And now we're done. Since we've shown if h of x equals h of y, it follows that x equals y. Any questions? Okay, so that's what kind of more formal proof of injectiveness would look like. So that handles this one. Okay. So that brings us to B then, where now we've got two functions f and g, each of which are injective, and we're trying to show that j, therefore, which is defined as the sum of two functions, is injective. And so I should say that these statements might be true or they might be false. So that's kind of, and these are the hardest things to do. So the first step is to decide what you're trying to prove, whether we're trying to prove this is true or whether we're trying to prove that this is false. So any thoughts on this statement in B?
It seems like it wouldn't necessarily be true.
Can you think of something that might violate this?
Yeah, like if f gave you 3 and g gave you 2, that's 5. If f gave you 2 and g gave you 3, that's still 5.
So we want to be careful. So yeah, but we want to think about maps in general, right? So yeah, your intuition is correct, that this is actually not true. So this is false. And if we want to prove that this is false, and this is what we'll get to a lot next time, then we just need to find one concrete, possibly counterexample, or at least show that a counterexample might exist. So that means we need to come up with two functions, f and g, each of which are injective, but the sum is not injective. And when you're trying to come up with counterexamples, my suggestion might be to think about like the simplest examples that you can work with, rather than try and cook up the most complicated thing. Does anyone have something that in mind that might disprove this? You're welcome to chat it into me if you're more comfortable doing it that way. That's fine too.
F of x equals x and g of x equals x plus 1.
F of x equals x and g of x is equal to
Negative x.
negative x. Yeah, that one would work. Yep. I think this is the idea, right? You almost want to pick like, when I'm thinking of counterexamples, that's what I do. I think of like, what are the easiest things to start with? So like, what is the easiest one-to-one function that I could probably think of would be f of x equals x, right? The identity function. And then you want to think about, okay, can I think of a function g which is also injective, so that when I add it to f, I'm going to get something which is not injective. And if you add these two functions together, you get 0, which is definitely not an injective function. This is the function that takes any input and maps it to 0. We have two injective maps that when we add them wind up being a not injective map. Okay, so maybe since we've got some time, this is the last one, and then we can come back and revisit 3, since I want to use some results that will prove in 4 to deal with question 3. I'd like to break you guys back up into, I'll put you into the same groups that you were in before, just to kind of see what sort of ideas you might have about trying to prove this one over here. So here it's kind of similar to the previous one, and that is what we're trying to prove is if P, then Q, where P is the statement that F is strictly increasing, and Q is the statement that F is injective. And I think like the intuition here, you might be thinking like, yeah, this is clear. Is there anything that I need to prove? Because if a function is only going up, it's going to be one-to-one. And that's kind of the right intuition, as we're saying, if a function doesn't turn around, then it's going to be one-to-one. But I'd like you to try and prove this a little bit more formally besides just a picture. So I'll break you guys back up into the same groups. If it's not an issue of hashing out like a fully complete proof, even if you've got an outline for a proof, that's great. I'll break you guys back up. Your rooms are open. Again, we're just working on this last statement C, and Nat and I will drop in to see how you guys are making out with that. So I know one group was able to prove it. I only got a chance to talk to one group, and they were able to prove this thing using contradiction, which is not necessarily the way that I was thinking about it, but it was a really nice proof. Did any groups do it differently? Use direct proof or contrapositive on this? Or...
We tried direct proof because I thought that's what you wanted us to do. We all felt that contrapositive would be easier.
No, yeah. So here, I would say from here on out, unless you're told do it this way, you're welcome to choose whatever method you want to do.
Oh, okay, we thought you literally said you wanted us to try direct proof.
Nope.
Okay.
Sorry if I said that. No, I
Misheard
didn't mean
then.
to say that if I did. And so you tried a direct proof, but are not happy with it.
Well, I mean, we think our logic is sound, but we're pretty sure that I guess the syntax or the terminology we used is not really appropriate.
Okay, well, I think I'm gonna have to leave us with a cliffhanger because I realize we're at 3:15. So maybe we'll pick up with this one to start things off on Wednesday. We can compare. I'm happy to we can take a look at what you did at the start, see if it looks good, and we can take a look at what some groups did with the contradiction, and before moving on to the next material. So we've got one more bit of material that we're going to cover before our exam. Our exam is next Wednesday, so it's a week from Wednesday. So we'll cover some stuff on Wednesday dealing with proof and disproof. We have seen that a little bit today. And that will be the end of the material that will be on exam 1. So on next week's plan will look like Monday will be review for the midterm, and then Wednesday will be the midterm. So sorry to end things with a discussion about an exam, but we do have an exam next week. So before Wednesday's class, there is a reading quiz that I'd like you guys to do that will introduce you to some of the stuff we'll talk about on Wednesday. So otherwise, thank you all for a nice class. I'll see you guys on Wednesday. If you have any questions, feel free to stick around. I'll stick around.